Hi students, it's Mrs. Gifford here, and today I'm going to talk to you about section 9.6, exponential functions. After today, students will be able to identify and graph exponential functions. So before we can practice that, let's talk real quick. What is an exponential function? Here's your equation right here. And exponential functions are in the form of y equals ab to the x power. A can't be 0 because that'll just make everything 0. B needs to be bigger than 0. And B has to be something other than 1. In this case, here are some examples of what exponential equations look like. Okay, different than quadratic equations in that a quadratic has x squared term in it. Okay, x squared term. The big key here is this exponent. In a quadratic equation, the exponent is a 2. In an exponential function, the exponent is a variable. The graphs are also different. The graph of an exponential is kind of a swoosh, if you think of like the Nike symbol on tennis shoes, as opposed to a quadratic equation. We just got done working with U-shaped graphs with parabolas. So let's move into some practice here. We have this first one where we're going to graph the equation y equals 7x. We're going to talk about find the y-intercept, and then we're going to talk about the domain and range. So all we're going to do, I have this table here, and I picked the values, -2, -1, 0, 1, and 2. I picked those because they're really easy numbers to work with, and they're going to keep my numbers relatively easy to manage. So the first thing I'm going to do, this middle column, I'm just going to substitute a number in for the variable x. And in this case, we have 7 to the -2 power. And when you type that in, you're going to get the answer of 0.02. And then we have 7 to the -3 power, which becomes 0.14. Now, in case you're wondering again or need a reminder of how to put that into the calculator, you're going to hit the 7 key, caret, the negative key, and then 2, excuse me, and then hit equals, and then you get your value there. So continuing with this table, I put 0 in for x, anything to the 0 power is 1. Then I put 1 in, that gives us 7, and I put 2 in, that gives us 49. So we have everything we need now to make our graph. And as we're taking a look at the grid, my first coordinate pair is -2, 0.02. -2, 0.02 is right here. It's actually super close, almost sitting on that line. My next coordinate pair is -1.14. That needs to be just a little bit above it. But again, my y-axis is counting by 2's, so it's going to be super, almost like they look exactly the same. But the separation now is going to happen when we have x equals 0. Our coordinate pair there is 0, 1. Again, my y-axis counting by 2's, so my 0, 1 is there. My next coordinate pair is 1, 7. Over 1, up 6, there's 8, so 7. And then my last point is 2, 49. 2, and then all the way up to 49. So from here we can connect our points. Again, we're going to make this Nike swoosh-esque type curve. And if we were to continue that graph over there on the y-axis, it would keep getting closer and closer and closer to the y-axis, excuse me, the x-axis, but it would never touch it. So the nice thing about creating a table using the number 0 is that you have found your y-intercept. So in this case, the y-intercept is 0, 1. And now we need to talk about the domain and range. Well, the domain is just what values do we put in for x. In this case, the domain is all real numbers. And the range, well, we have to take a look at what happens with the y values. In this case, as I said, these numbers, if we keep going to the left, we get closer and closer and closer to 0. But it'll never touch 0 and go into the negatives. But we see that it's on the positive side, so we can say that the range is all positive numbers. Now, the next thing to do with this graph is we're going to use it to find the approximate value of 7 to the 0.5 power. So what do we need to do here? We're going to take a look at the 0.5. That means x is 0.5. So on our graph, we're going to go over to 0.5 on the x-axis and then go up to the graph to find our approximate value. So 0.5 up to there. And I would say the approximate value when x is 0.5 is 4. So y is approximately 4. Again, how did I find that? Went up to the line, and then I went over to the y-axis, and again I'm counting by 2's, so that's why it ends up being 4. Let's get another example similar to that, but the difference in this one is we have a base number as a fraction, and we're going to subtract 1. So we're going to make a table just like we did before, and as I did before, I just picked the values for x, -2 through +2, and I'm going to take the x out and put these numbers in. So I have 1/2 to the -2 minus 1. Type that in, you get 3. Now I should also remind you to type this into your calculator, use the parentheses key, your 1 key, the division symbol, 2, caret key, negative, and then whatever your number is, and then you can do subtraction and hit equals, and you should get these values. So continuing, I take the x out and I put -1 in, and this one gives me 1. And then I have 1/2 to the 0 power minus 1. Anything to the 0 power is 1. 1 minus 1 is 0. And I put 1 in. 1/2 to the first power is 1/2. Minus 1 is -0.5. And I've got 1/2 to the second power, which is 1/4. 1/4 minus 1 is -0.75. So just like on the previous slide, we have this table. We're going to make this graph. In this case, one observation you might have is that these numbers are decreasing. So our swoop is going to be going a different direction. But let's graph our points. So I've already set my scales up on my axes. My first coordinate pair is -2, +3. Then I have -1, +1, 0, 0. And then I have 1, -0.5. So over to 1, down to -0.5 is here. And then over to 2, down to -0.75 is here. And then we're going to connect these points to make our swoosh. And as we look at this graph, notice these points are getting closer and closer and closer to -1. So going back to the directions, we're going to graph it, and then we're going to talk about our y-intercept. And just like with the other example, I have my y-intercept in my table because I chose to use x as one of my values. And let's talk about the domain. There aren't any restrictions here on what x value we can type in, so we're going to say the domain is all real numbers. And in this case, the range is the one that's affected, and the range are the y values. So what do you notice? Going up to the left here, this graph is going to keep going up and up and up. But as the graph goes to the right here, it's going to get closer and closer and closer to -1, but it's not ever going to pass it. So what do we say about that? We say the range is y such that y is going to be greater than or equal, or not greater than or equal to, just greater than, y is greater than -1. This graph will continue to approach -1, but will not ever get to it. All right. So now we're going to take what we've talked about with exponential equations, and we're going to apply that to this situation. It says a certain bacteria population doubles every 20 minutes. Beginning with 10 cells in the culture, the population can be represented by the function b equals 10 times 2 to the d power, where b is, can you hear the announcement? Sorry about that. B is the number of bacteria and t is the time. So first of all, let me back up a little bit. This word culture right here is like a sample. If you've ever gone to the doctor and you've got tested for strep throat and they put that little Q-tip in your throat and they get some bacteria out of your throat, that's called a culture, and they use that to test to see if you have bacteria. All right, so going back to our problem, Here's our exponential function. We have b equals 10. B for bacteria, 10 is our initial value. 2 because it doubles, and to the t power. So in this case, it says the time is counted in 20-minute increments, and we need to figure out how many there will be after 2 hours. So we need to figure out how many 20-minute increments are in 2 hours. Well, in 1 hour, it's 3 20-minute increments, and then in 2 hours, it's 6 20-minute increments. So in this case, we're going to take this 6 and we're going to substitute it in for t into our equation to see what happens after 2 hours. So b equals 10 times 2 to the 6th power. Following order of operations, we do the exponents first. So we get b equals 10, and 2 to the 6th power is 64. And multiplication, 10 times 64 gives us 640. So we figured out, using this particular bacteria, this particular culture, after 2 hours it goes from just 10 bacteria to 640 bacteria. Okay. All right, last example. So we've done a lot of work with, especially linear equations, with trying to figure out if it's linear or not linear. And with quadratics, we know if we multiply by a certain value, we know then that becomes a quadratic equation. In this case, or I should say a quadratic equation. Sorry. So in this case, we need to take... Lost my train of thought, folks. I'm sorry. So let me go back here. So when we talked about linear equations, we talk a lot about recognizing how it's linear by what's happening in a table or making a graph. We're going to do the same thing with exponential functions. And so I have this table here. And just like when we look at linear equations, we look to see what kind of a pattern happens in the table. So we need to take a look at, if working backwards actually, I'm going to do 16 divided by 12, I get 1.3. And then I get, then I'm going to do 20 divided by 16. Oops, I didn't even write my 16 divided by 12 back here. All right, so let me go here. 16 divided by 12 equals 1.3. And then I have 20 divided by 16 equals 1.25. And 24 divided by 20 equals 1.2. And we can continue going through this to determine what happens by looking at this pattern. So as we see it, we notice that there isn't really anything going on here that's the same with that. But if we look closely, going back here, what do you notice you do to 12 to make 16? I add 4. 16 to make 20, I add 4. 20 to 24, I add 4. So this one is not exponential. Actually, this one is linear. So let's check this out by looking at a graph. We're going to graph these coordinate pairs in the table. And so we're going to go from 0 to 12. And I've got 3 up to 16. And I've got 6 up to 20. And 9 up to 24. And if you look closely, these are definitely not swoopy. They are linear. So in this case, by graphing, we can also, oh, that's a really bad line, sorry. We can also determine that this is not exponential with the fact that our lines or points actually turn out to be in a straight line. If it's swoopy, it's exponential. If it's a U shape, it's a quadratic. If it's a straight line like this, it's linear. So hopefully by now you can determine if something is exponential or not, and also now you have a great idea about how to graph exponential equations.